Number 66. Calculate the ratio of the heights to which water and mercury are raised by capillary action in the same glass tube. All right, so they're talking about heights and capillary action. We need to know the formula that relates height to forces of capillary action, and that's going to be the formula over here on the right-hand side. All right, this formula says that the height a certain fluid will reach in a small tube will be equal to 2 multiplied by the surface tension of the fluid multiplied by the cosine of the contact angle between the fluid and its environment, right? In this problem, that environment is glass. Then divided then by the density of that particular fluid multiplied by gravity, then multiplied by the radius of the tube. So now we basically have we're trying to find the ratio, right, of the two heights, and we realize that they're going to be in the same type of apparatus, right? So if you had an apparatus that looked like this for, let's say this was for water in here, this same apparatus now would be used for mercury. So let's just say, for example, this is the level now of water inside of this basin. Okay. Now we know that water is going to enter this particular tube, but we don't, you might know, and that's great, but I'm just going to assume we don't know how high this water will go. Maybe it'll go only up to here. Maybe it'll go all the way up to here, right? That's the whole point of these calculations. Similarly, we're going to have the same scenario now, right, for the mercury, where the mercury will assume, starting here, the mercury is now filled up in this tube. And again, we don't know how high it's going to go in this small tube via capillary action. Maybe it'll stay down here, maybe it'll go all the way up, whatever. We're trying to figure that out. We're trying to figure out the ratio, okay? So now they said calculate the ratio of heights to which water and mercury are raised by capillary action. Now, it says to which water and mercury. It doesn't tell me, though, specifically what ratio they're looking for. It doesn't tell me that it's looking for the ratio of water to that of mercury. It doesn't say, it just says water and mercury. Right? You could reason out that it could be height of the mercury relative to the height of the water. I don't really know. All right? It shouldn't matter, though, in terms of the ratio per se. In terms of what the ratio means, it shouldn't matter. The answer will just be the reciprocal. But in terms of what the ratio means, it doesn't matter how you organize it. So I'm just going to do exactly how I read it. It's the height of the water relative to the height of mercury. All right. Yeah. So let's start plugging in now so the formula here. So this is the height, right? This is the height is a function of all of these things. But no matter whether we're talking about water or mercury, some of the things within this formula are constant. So let's just get rid of some of the constants first, right? 2, it's the same for both, so that'll cancel. All right, gravity, who cares? It's the same for both. The radius of the tube, they're identical here, right? So therefore, that'll cancel too. So that's gone. The only difference between the two, then, heights will be a function of the surface tension of the fluid, water versus mercury, the contact angle, water versus mercury against glass, and then the density of water versus mercury. So basically now what I can do is plug in those values, all right? So for the height of the water, it's going to be a function then of relative to the height of mercury. It's going to be a function of the surface tension of water multiplied by the cosine of the contact angle of that of water with glass, then divided by the density of water. That should then be divided now by all the values for mercury. The surface tension of mercury multiplied by the cosine of the contact angle between mercury and glass, and then divided then by the density of mercury. All right, all we have to do is now plug in the values. Surface tension of water, okay? What is it? Well, you got 3 values up here. Which one are you going to choose? Traditionally, we're going to choose this value, 20 degrees Celsius. Why? Well, we're assuming this is being done in the lab and it's at ambient temperature. How did I know that? I have no idea. It's an assumption, all right? You could argue that it should be at 0 degrees Celsius, right? A lot of things in terms of chemistry, standard temperatures and pressures and whatever, you might use this number. Okay, that's cool. You might say, no, it's really hot. I'm going to do it. I'm going to boil myself out of the room, all right? And you might choose that your water's at 100 degrees Celsius. All right, that's cool. But no matter what you choose, the answer will be different. Okay, so I'm going to choose the one right in the middle. All right, try to make everyone happy here. We'll try to cut it right down the middle. Anyway, just get to it, Andrew, right? So 0.07782 multiplied then by the cosine of that contact angle for water with glass, it's 0 degrees. Then divided by the density of water, that's 1,000 kilogram per cubic meter. Hopefully that's memorized at this point. And now this for mercury. So we got the value down there of mercury, right? Notice how they don't really give the temperature differences, but obviously it'll change with temperature. Times then cosine of theta. The contact angle here is 140 for that of mercury. And then divided now by the density of mercury, that's about 13,600 kilogram per cubic meter. So now all we got to do is just plug everything in, okay? And let's do that. So we have now 0.0782 times 1 essentially, because cosine theta is 1, then divided by 1,000. Take that answer now and divide it then by 0.465 times cosine of 140, and then divided by 13,600. And we get a value of negative, what do we have here? Oh, I realized I made a slight mistake. I'm just looking back over the numbers and I screwed up that, right? 0.0728, and here's I guess I'm dyslexic. So let's plug this in, 28. Okay, let's get that right. Let's recalculate. My apologies. So one more time, 0.728 divided by 1,000. I meant to say 0.0728. I don't know. I think you have to, today, there's enough problems. I think I did like 15 or 20 problems today. So this is my last one for today. 0.465 times cosine of then 140. Divided then by 13,600. And here we go. So we get that, yeah, I'm just looking over the numbers. That looks good. All right, so here, now the answer is negative. All right, but let me not plug in the negative sign yet. Why? Well, let me write out this. So this is, considering rounding, is 2.78. 2.78 divided by 1, all right? So that's what the division means. It's 2.78 units of length to that of 1 unit of length for the mercury. The question is, where should the negative sign go? Should it go here? Should it go here? Right? Both numbers are negative. Right? Or I should say the ratio is going to be negative no matter what, but I think it actually has some meaning as to where this negative sign will go. Well, where does the negative sign even come from? It comes from the cosine of 140, that's negative. So if you notice, that cosine of 140 is the contact angle for that of mercury and glass, and therefore I'm going to keep this negative sign with the mercury because it's going to make this make more sense, all right? So this is my answer, and then what this tells me is that the water will rise up positive 2.78 units of length above its level of water inside the basin. 2.78 what units? Could be meters, centimeters, whatever, as long as you're consistent. This is a ratio, so basically it's unit less. So you can choose whatever units you want, as long as you're consistent. So let's say that the water goes up to this particular level up here, right? So the water is going to fill this tube, and this right here is going to be, actually, let me draw the arrow. That right there is going to be a positive 2.78 units of length relative to, let's take a look now at the mercury. It says that it's going to be negative 1. Negative 1 to what? Well, negative in relation to the level of mercury in this basin. So now it's going to be down here somewhere. Okay? And the mercury is not going to go past. And this negative 1 now signifies this distance. Well, that's really messy. Let me choose a slightly different color. This distance right in here. Okay? That's going to be now the value of the mercury in the tube relative to that in the basin. It's negative. So that's what it means. All right, that's the ratio. I would suggest you think about it in terms of don't place the negative in the numerator. Although mathematically they're the same, they have a different physical meaning. Anyway, guys, thanks for tuning in. Hope this helped. Please remember to subscribe. We look forward to helping you out with more problems. Take care.